Lecture 7 on Energy Conservation and the Forms of Energy. The forms of energy, or energy systems, are lumped into two main categories. Mechanical energy, such as the energy of something falling, the kinetic energy, kinetic Greek for motion energy, or speed energy, such as a ball falling to the earth. The ball has a potential, depending on how high you raise it, to fall. The higher you raise it, the greater potential energy it has. The potential energy from gravity, or UG. There's spring energy, or US. The spring is giving the arrow potential to shoot at great speeds. Greater potential the farther you pull it. Greater potential the farther you stretch a spring or compress a spring. Non-mechanical energy would be lumped into the category of thermal energy, the energy from friction, drag, air resistance, any type of rubbing and make something warm up. Thermal energy is sort of a catch-all for all non-mechanical, all non-potential and kinetic energies. Other forms of energy, such as chemical energy, we'll deal with in 222, but this is electrical energy, mostly at the atomic and molecular basis. Or nuclear energy. When a large object is lifted up, we increase its potential energy. The potential energy depends on how high we lift it and how heavy the object is. A more massive object requires more potential energy. The higher it is, the more potential energy it requires. So potential energy is a product of both the mass of an object being lifted and the height it's lifted to. Potential energy can be thought of as the energy that something has when it releases from its fall. The more massive the object, the more potential energy it has to fall and hit and hurt something. The higher it is, the more potential it has to fall at greater speeds. Gravity creates the potential for something to fall from a high state to a low state, such as the top to the bottom. We call this the gravitational potential energy. It depends on mass, gravity, and vertical position, the height, or y. The zero of potential energy is arbitrary. You can place the origin of your coordinate system, your ruler, wherever you choose. Thus, the zero of potential energy equaling 0 joules, is wherever you choose it to be, and be assured of getting the correct answer to a problem. Only the change in potential energy, the delta, has a physical significance. As always, the change of something, the delta in physics, is what is most important. Potential energy, in and of itself, thus, is not important in its value, but the change of potential energy, which depend on displacement, on the vertical displacement, is physical. Another type of potential energy is the potential energy of a mass on a spring, or a mass spring. Potential energy mass spring relates to how much a spring is stretched or compressed, but how much it's stretched or compressed by the square of y. We can set y to be 0 at the equilibrium of the spring, and y can be 5 centimeters or 10 centimeters away from equilibrium by a stretch or a compression. 1/2 ky squared is the potential energy of a mass spring. Depends greatly on how much a spring is stretched or compressed, since it depends on y squared. K is a property of the spring only. The spring constant K would be the material that the spring is made of, and how tight the windings are. Is it made of steel or copper, or is it rope or string? PE mass spring does not depend on the mass. Once a mass has been hung from a vertical spring, that becomes the equilibrium, which you're free to choose as the 0 of the PE system. The potential energy equaling 0 is arbitrary. The changes in potential energy, depending on the displacement of the spring, the delta y, from the equilibrium, is physical. kinetic energy or speed energy depends on the mass that has kinetic energy, the mass that is speeding, and the square of the speed. The velocity, positive or negative, the sign of the velocity, positive or negative, its direction, goes away. Negative velocities get squared away. So kinetic energy does not depend on direction. In fact, energy is a scalar. It's a number. It's a magnitude. It is not a vector. Energy, such as kinetic energy, doesn't depend on direction. Because negative velocities get squared away, kinetic energy is always greater than or equal to 0. There can never be a negative kinetic energy. We can have negative changes of kinetic energy, a negative delta Ke, a loss of kinetic energy, just as we can have a positive delta Ke, an increase in energy, an increase in kinetic energy. In summary, potential energy and spring energy depend on displacements from the center of the Earth and displacements from equilibrium, respectively. They're associated with potentials, are associated with positions of objects, positions vertical from the center of the Earth or from an equilibrium. Kinetic energy can come in two forms. The form we're dealing with is called translational kinetic energy. You translate from one position to another as something is moving, just as you translate from one language to another. Rotational kinetic energy is just that, the kinetic energy when something is rotating or spinning. We'll deal with that in Unit 3. The non-mechanical energy, thermal energy, relates to friction. The rubbing or friction increases the molecular motion. The friction of your hands is making the molecular motion of your hands vibrate more. The atoms and molecules attached with their bonds are like balls on springs that vibrate more when surfaces interact via friction. The increase in the random motion of atoms by objects by friction is an increase in their thermal energy. We can analyze energy. Energy is analogous to money. There's no unique definition of money. Potential energy is like a savings account. The more of a savings account you have, or the less of a savings account you have, the amount of money you have in the savings account is only important if you can get the money out. If you have $1 billion in your savings account, but you can't get out any money, then you're just as poor as someone with no money. The value of potential energy, like the value of the savings account, is not important, but the change in the potential energy, how much potential energy you can be released, just as how much money you can take out of your savings account, is what's physical, is what's important. The change in potential energy can become kinetic energy. The potential energy can be exhibited by changing into a form of increasing or decreasing something's speed, increasing or decreasing something's kinetic energy. So kinetic energy would be the spending of potential energy, the spending of a savings account like cash. Work is a change of energy. So work would be like a paycheck, an increase in energy, or a decrease in energy like paying the bills or a withdrawal. You can add or remove money to a system. You can have positive or negative work adding, negative work taking away energy from a system. Wealth can only be exhibited by spending, by transferring money. You need money to make a living. Transfer money is a change of energy, which is what work is. Need to do work, transfer energy to make a move, to have motion. The Greek energy is the Greek word for doing work. So we keep track of money spent and earned. Like a good accountant, we can keep track of energy lost and gained. A good accountant can see where energy is conserved by accounting for all the objects in the interaction. Connecting the previous chapter, impulse, to energy, we know that cars drive in one dimension is very dangerous and eventually they collide. Which collision has greater impulse when the cars stop afterward, when the cars bounce off each other? We've analyzed in the lecture on momentum that cars bouncing have a greater change in their momentum from stopping and then bouncing compared to just colliding and stopping. So the elastic case, the bouncing case, has a greater impulse. But which collision is safer to be in? When the cars collide and stop, we know that's worse or more dangerous than when the cars collide and bounce off each other. Bumper cars are safe for children to play. The bounce is much safer. An elastic collision is much safer. An inelastic collision where they smack into each other and stop is often more dangerous. In terms of energy conservation, we can see why. If cars have a perfect bounce, a perfect elastic collision, they lose no speed. They bounce back to the same speed they came in with. Therefore, they lost no kinetic energy, and therefore they lost no mechanical energy. If there's no change in their height or any springs involved, then there's no change in any energy form. No change in mechanical energy if they return with the same speed. Same kinetic energy in, same kinetic energy after the bounce. If the cars smack into each other and stick in an inelastic collision and they stop, all the kinetic energy has to go somewhere. Where does it go? Into the sound, into the fire, into the breaking of parts. That's all thermal energy. All the energy is lost. The kinetic energy is all lost to the environment. Hence, it's more dangerous to be in an inelastic collision, a collision without a bounce, because the energy is not preserved. It goes into breaking things. But in both cases, momentum is conserved. But only in the elastic case, the bouncing case, is the mechanical energy conserved. So a moving object, therefore, has at least two special quantities associated with it, momentum and kinetic energy, and they are entirely independent. Momentum concerns the speed and direction of a mass. It is a vector. Kinetic energy is just a number, or a scalar. A moving mass always has kinetic energy and momentum. There is conservation of momentum and is independent of conservation of energy. In a collision, we can calculate how much kinetic energy gets lost. The momentum is still conserved, not the kinetic energy. Perfectly elastic, a bounce means no thermal energy gets created because the system kept all of its kinetic energy. None was lost. Without the creation of sound, or breaking things, or fire, just a perfect bounce, there's no energy to give to create those things. Sound also becomes heat. It is another form of thermal energy. A perfectly elastic collision would be like a game of billiards or pool. They bounce off without losing their speeds. Two objects incoming with the same momentum collide and bounce off each other, equal and opposite impulses, and the momentum is preserved. They income with the same momentum as they leave. No kinetic energy has been lost. An elastic collision. The net kinetic energy has not changed. So the energy is conserved. Equal and opposite momentum before and after. The system does not lose momentum. The impulses are equal and opposite. So momentum is conserved, and independently energy is conserved. In an inelastic collision, the kinetic energy has changed for the objects and for the system. The total kinetic energy has changed. It has been decreased or perhaps entirely lost. Mechanical energy is not conserved. The momentum may have changed from before and after, but equal and opposite impulses or change in momentum means momentum is still conserved, even though energy is not conserved. Momentum conservation and energy conservation are independent. In Newton's cradle, the balls bounce back and forth, but when one ball gets lifted, a ball on the opposite side bounces up with the same momentum that the ball 1 had before the collision. Ball 5 has the same momentum that ball 1 had before the collision. Then ball 5 will bounce back, hit, and make ball 1 have the same momentum that ball 5 had and ball 1 originally had. What you can never have the case is ball 1 will never deliver its momentum to both ball 4 and 5. Both ball 4 and 5 won't lift off with half the velocity. And ball 4 and 5 won't smack back down to the cradle and make ball 1 bounce up with twice the velocity that 4 and 5 have. This will never happen. Ball 1 will always make ball 5 lift off after the collision with the same momentum that ball 1 had, and 5 will return to the cradle, knocking ball 1 back up with the same momentum that 5 had and 1 had originally. This is a consequence of both kinetic energy being conserved in an elastic collision and momentum being conserved. Why? For momentum can be conserved, if the balls are the same mass, they have m times v for ball 1, the same mass of ball 5, therefore gives m times v to be the same velocity, same mass. Because kinetic energy is also conserved, 1/2 mv squared coming in for ball 1 equals 1/2 mv squared leaving for ball 5. If the second situation, part C, of ball 4 and 5 were able to leave, two balls leaving with half the velocity, then v squared for ball 4 and 5 and 1/2 mv squared would not be the same as the incoming kinetic energy. Work that out. Be aware when we talk about the system's momentum as conserved, when we talk about a closed system, we are not referring to a closed energy system. We have independent means of describing open systems for momentum and open systems for energy, and closed systems for momentum and closed systems for the independent phenomena of energy. A bowling ball, or a mass on a string, a bob swinging back and forth, is another example of energy being conserved, exchanging between two different forms. When the bowling ball is lifted up, as long as anything is lifted up, its potential energy, gravitational potential energy, is increased. When the bowling ball is released, it swings down. When the bowling ball goes down, its gravitational energy decreases. PEG decreases, as you see in the box. The energy then increases in the form of kinetic. When something drops in height, the gravitational energy decreases. Some other form of energy must increase in the same proportion for energy to be conserved. The position energy or the potential energy decreases, and it goes into the motion energy or the kinetic energy. Delta PE, the loss in gravitational energy, is equal to the increase in kinetic energy. As the pendulum swings back up, the gravitational energy increases as going up, and the speed decreases, the kinetic energy decreases in exactly the same proportion. And this can repeat over and over again, like the cradle in the last example, going from a max to a min of gravitational energy, and an equal but opposite min to a max increase in kinetic energy, and so on. Let's do an example of potential energy being conserved and its transfer to kinetic energy. A 500-gram block on a frictional surface is pushed against a spring with a spring constant of 200 newtons per meter, compressing the spring by 2 centimeters. When the block is released, at what speed does it shoot away from the spring? Well, we've changed the spring energy by compressing it. The spring energy changes again when the spring gets released to launch the block. So the spring gives its energy, the energy it had by being compressed. It releases its energy, or a negative delta PE spring, a loss of spring energy, goes to an increase in the motion or the kinetic energy of the block. We then set up a form of spring energy and equate it to the increase in kinetic energy, keeping the track of the negative sign for the loss of one form of energy, the increase in the other. And then we can solve for the change in speed, which is what the change in kinetic energy relates to, and solve for the final velocity when the initial velocity is 0. Complete this problem on Blackboard. We don't really know what energy is, but we can think about energy as a number when a ball, such as a ball being dropped, it has a total energy or a number. The greater the ball, the greater the height of the ball, the greater the total energy. The greater that number will be transferred into its speed. No one really knows what energy is, but we can think about it as a substance like a fuel filling up one form while draining away from another form, such as a loss of potential energy as a form of energy. The energy goes, that substance of energy fills up another form, such as kinetic energy, as something falls to fall faster. These are just models or ways of thinking about it. You can read the rest of these slides as a PDF or by pausing the screen.